So we are told that for a sample of 260 homeowners, 105 say that they own at least one dog. Trying to figure out the true proportion of homeowners who own one dog here. And I have given us a couple of other assignments beyond just do the confidence interval, because that's just like the button press away. I've also said what is either the relevant T or Z score, and then what is the E. So for this problem, let's start with just this first one here. So the Z of alpha over 2, or the T of alpha over 2. Which one do I need? Do I need a Z score, a T score, or does it not really matter?
A Z score. It's over 30.
So our N is over 30, which means we can use the Z score. Why are we allowed to use the Z score when our N gets big?
Because it's almost the same.
Yeah, because it becomes basically the same thing as the T score because it gets really, really close to the normal distribution. Good, that's perfect. And so could we use the T score?
Yes.
Yeah, absolutely. And it's going to give us about the same answer. There's no reason why we could not use the T value here. It gives us about the same thing. And in fact, what is the Z score that we have for this? 2.58. And then, did anyone do the T score? Did anyone find the T score that goes, yeah, that's 2.595. So this is like 2.584 or something. And then the T is 2.595. So again, like, are they the same value? No. Are they really, really close? Yeah, they're very, very close to being the same value. I have seen a couple of people use 2.56 for 99. That is not 2.58 for 99. And if we're not sure, we could do inverse norm in order to figure that out. With 0.99.
For the T. As you did 2.
You do inverse T. So we did
Yeah.
inverse T.
The area.
What would the area be?
Oh, you have to put it in the different way. It'd be like 0.003.
Right.
I did it wrong.
So you have to take that 99%. We have 1% on the outside, split it in half, so 0.005. And then the degree, how many degrees of freedom would we have here?
104.
I think the total sample size, 250. 250 degrees of freedom. Oh yeah, it's good. And they're again both very, very similar, so it should use. We're gonna get it out. It'll be slightly different, but not different enough for us to really take much notice. All right, we also needed the error. Before we get into like the specific proportion formula for error, if I just want the generic way that I calculate error, how have we done margin of error before? What does this look like?
T score.
Yeah, that Z score or the T score, depending on which one.
Times.
S
Over the square root
of it. And that S could also be sigma, if that's what we were given. But in this case, we're not given it, we're given S. Or we're not actually even given anything. We're going to be able to calculate S. So how do I find S? What is missing here?
P and Q.
Yeah, we need to take P and Q. We're going to take the square root of P hat times Q hat. Okay, well, what is P hat going to be? 0.4004. How'd you find that, Liz? 5 divided by 260, which equals, I totally agree, 0.404. And then how do I find Q once I know P?
1 minus.
1 minus. Which is equal to 0.596. Ethan did this slightly differently. Ethan instead did 260 minus 105 to get 155, and then did 155 out of 260 in order to get Q. Would that work as well? Yeah, if 105 own then 155 don't own, so it's 155 out of 206, out of 260 to give us the exact same. Yeah. So either way, they're totally fine. Fantastic. So we have everything that we need in order to do this. So this is going to be 2.58 times our S, which is the square root of 0.404 times 0.596 divided by the square root of 260. 2.58 0.44 times 0.6, and dividing that by the square root of 260. 0.0785, we'll call it 0.07. You might get slightly different values depending on where you rounded, where you didn't round, or so on. So for instance, I rounded this z-score. If you used a precise z-score, you might end up with something different. I rounded these decimals. If you didn't round them, you might end up with something slightly different. I did not round the square root. If you took the square root and then rounded, you might end up with something slightly different. But as long as we are in the ballpark of that, then we are happy. Questions here? With our z-score or t-score, both of which are fine in this case, or with our getting the all that feels comfortable, fine. When we see this on the test on Wednesday, we're gonna knock it out of the park. Everyone's gonna get hundreds.
I'm down.
All right. So then the last thing is what the question is actually asking for, which is confidence interval. Two different ways that I can do confidence interval. I can either use my z interval or my t interval. Either way is fine. From before. If I want to use that z interval or the t interval from before, what am I going to use as my x bar? What is my quote unquote mean here? Yeah, it's just p, which in this case is our 0.404. So if we want to use the old test, which we totally can, this is what we use as the mean. If we don't want to use the old test and instead want to remember a bajillion calculator functions, what is the new calculator function that we had that kind of processes it for us?
It's like
So z interval would work where you could plug in p hat in for x bar and you could plug in the 0.491 for s. Totally would work. 100% would give you the right idea. One prop z interval will do that work for you. Oh wow. There's a lot to unpackage there. Where in this case, we are just plugging in what do we want for our x, how many successes do we see out of how many, and it runs all those calculations for you. So this would give us.
Is it like stat calc, right?
Stat tests.
Stat test.
Yes.
Okay.
And so what we see is from 0.325 up to 0.4H2. If we needed to interpret this as a interpret what this means. What does it mean that we have a 99% confidence interval that looks like this? Okay, so 99% of our data falls between those two values. That is certainly true. But what is our interpretation for the confidence? What can we say about the true percentage of people who own at least one dog? What Wesley said here, totally correct. Technically speaking, that is a confidence level, not a confidence interval interpretation. This is like the annoying part of statistics where it gets very linguistically finicky and annoying. Like, yes, totally correct. Also not what the interpretation piece is, even though it's a correct interpretation. This is the annoying part of sense. We are 99% sure that what?
That homeowners own these ones.
We're 99% sure that homeowners own, what percentage of homeowners to what percent of homeowners?
0.3.
So we are 99% sure that the true proportion of homeowners who own at least one dog falls between 0.325 or 0.482, or as Liz said, we are 99% sure that somewhere between 32.5 and 48.2% of homeowners own a dog. Either way, so
Write that out, or will it be?
potentially on the SDC test. On the SDC test, you might, yeah, I don't know exactly what the formatting is. I think it might be multiple choice. Less than 2 weeks. 2 weeks from yesterday. So. For the very first one. That way we can do fun things like calculus with our. Yeah.
This one.
I lose my classroom after this in years later.
So are there people that think like we count us like in percentage of these two and we're not doing regular stuff? Are there?
I don't think anyone who. No what? No one that I know of who got their pre-cal credit is currently taking that. I have a lot of people in here who passed pre-cal last year who are in here again, but no one I don't think doubled up. All right, questions about our example? How are we feeling? Not too horrible. Pretty much exactly like what we were doing in 6.1 and 6.2, which you guys did really well on, so. Fairly reasonable. One more example to look at. We didn't have an opportunity to do this with 6.2 for reasons we'll unpackage here in just a moment. And that was the question that we looked at the end of 6.1, which is if I know what I need my error to be, can I calculate what my sample size would have to be in order for me to get that error that I made? So just a reminder here, we had our formula for the error that was the EBM equal to our z-score times either sigma or s, either way, depending on what we're given. And we took this formula and we solved it for n. And in doing so, we got that n was equal to, in this case, the z of alpha over 2 times s divided by that error, all squared. It's like the very end of 6.1 to find the sample size that we. Now before in 6.2, we couldn't do this. And the main issue that we run into if we try to do this with t-scores rather than z-scores is that we don't know what z-score or what t-score to use if we don't know how many degrees of freedom. Right, the value of t changes based on the value of n, and so if I don't know what n is, I can't know what t is, and then we're stuck. So we weren't able to do this with 6.2 because we couldn't find an appropriate t-score to just like guess with. And so we're going to instead need to, well, not instead, but we are back to being able to do this with our 6.3 content, assuming that n is big. If we ever get an n value that isn't large enough, then I guess our process just doesn't work and it's invalid. But assuming that we can get a large enough value of n here, then we should be good. And we'll see that the values of n that we're going to see with these examples are quite large. These are going to be fairly significant. All right. So let's go through. In order to find n, we only really need 3 pieces of information. We need the z-score. What the alpha over 2 is. We need to know the standard deviation. And then we need to know the error. And as far as like standard deviation goes, how do I find my standard deviation? What's that going to look like? Square root of.
Well, oh,
He had. Great. All right, 95% confidence interval. What is our z-score? 1.96. If I didn't know that, I would go to second bars, inverse norm, 95% center. What is my value of p hat here? How would I find that?
area, like I put 0.95. And so it's, but I'm unable to like, it says error. And I'm trying to get the z-score.
Are you an inverse norm?
Yeah,
Are you an inverse norm inside of inverse norm, or are you just an inverse norm?
Jeff.
Okay, we'll take a look after we do these examples.
Oh, no. I mean, I gotta get it.
2%, 20.
So let's do this. We're looking for our proportion of success, our likelihood of success. So in this case, we're trying to figure out the number, the percentage of people who have high-speed internet, and what percentage of success do we have to work with? That 40%. Okay, so that proportion in this case is going to be what we saw from a previous study, which is the 0.40, 0.4. Quick note, the reason why it has to be a previous study is because we haven't run our study yet, so we don't know what the proportion is that it's going to tell. Okay, so we have to pull from past data. What is our Q hat going to be? 0.6 or 0.60, 60%. And so this should just be the square root of 0.4 times 0.6. And then what do I need to be true about my margin of error? How much error am I trying to allow myself to have? 2%, so 0.02. And so now it's just a matter of plugging into the formula that we have. So n is equal to, so our z-score here is that 1.96 times s square root of 0.4, 0.6 divided by our error 0.02, all squared. Okay. So this is
What do I type underneath the denominator?
what is the error that we are trying to keep ourselves within?
And so, yeah, so it's like you typed in 1.96 times the square root of 0.4 to 0.6.
Yes.
Divided by,
Yeah, what is the, in the question, what is the amount of error that we are trying to stay with?
2%.
2%, so 0.002. Yep, exactly. So 1.96 times square root, we said of 0.4, 0.6 divided by 0.02. And we are squaring this value. I get 2,304 0.96. Which feels large, but they're gonna be fairly large. Now, is 2,304.96 a valid sample size? Can I collect 2,304.96 points of data?
Nope.
No. So what do I have to do to this?
Rounded. to the nearest.
Round it up to the nearest whole number.
Yeah.
For instance, if this had said 2,304.16 instead of 0.96, where would I have rounded it? Would I round it up or down? Always up. This value that we're calculating is the minimum value that n is allowed to be. Any smaller than this, and we're not getting the answer that we want, so we can only go up. We go up to the next. Okay. So hopefully very, very reminiscent of what we were doing in 6.1, which you guys all did a really good job. Questions with this first example? How- Get that sort of resounding positive affirmation. Okay, this is the cool part, because this was like one that I wasn't 100% sure on why, but there's like a cool train of thought that takes us to why we're doing this. And that is the question of, what do we do if we're the first ones studying this? There is no previous data to pull from. And how do we make sure that we pick a sample size that's big enough for us to be comfortable with the amount of error that we are seeing?
But we can't predict because the data rate starts. That's built. That we infer based on what we're getting this mass.
Well, so this is saying, like, there isn't previous data, we're going to need to figure out a way to do it. Yeah, so that's what we're going to need to do. First question that I want to address, what information did the previous example give us? So when I was going through here, we had this previous study that we looked at. What did we use that previous study in order to get? So that was how we got p hat, and ultimately we used p hat in order to calculate q and then an s. Right, at the end of the line, the thing that we are looking for here is this value of s. And the thing that I would like to note, we're trying not to make any assumptions about the data since we don't know what's going on with the data. Right. Which means if we guess that s is unnecessarily small, then we might get a smaller value of n than we want. And so we need to ensure that s is as large as possible. Our goal for making sure that we don't make any mistakes when we don't have previous data to pull from, we are going to try to maximize the standard deviation, that value of s. Okay, this is actually a geometry problem, or an ACT geometry problem even. If I have a rectangle and one side is p hat and one side is 1 minus p hat, which is like exactly what we're doing, right? If I'm considering the area here by multiplying these two things, that's like multiplying p times q. Question is, what shape is going to maximize my area? What would my side lengths need to be here in order to get the most area from this kind of fixed perimeter that we have? Maximize s. S is derived by multiplying these two quantities together. We could turn this into a geometry problem. How do we maximize this area? What shape would we need in order to maximize it? Should we make P really, 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 really small and 1 minus P really, really, really long to kind of stretch it out really thin? Should we do something else? What should our approach be to maximize it? Make it equal, make a square. A square takes perimeter, and that is like the maximum amount of area that you're going to get for that perimeter. If I need these to be equal in order to get this value to be maximized, what should P hat be equal to?
0.
Exactly. P hat is equal to 0.5. And then what should Q be equal to? Also 0.5.
Yeah, because like at first I typed in 0.01 times 1 minus 0.01, and I got 0.0099.
Which is very small
And then
compared to something like this, which is going to be large. And this is in fact as large as it can be.
And then I did 0.99 times 1 minus 0.99. And then I got 0.0099.
Yeah.
So but I did, for the third time, I did 0.5 times 1 minus 0.9, and I got 0.2.
Yeah, which is as large as the driving is. For instance, if we were to compare like what we get under the hood here, this would be like 0.24 versus like the 0.25 that we're getting from this, which is great. Okay, so if we don't know data, if we are just having to guess as to what P hat is, we're not actually guessing that P hat is 0.5. That's not really what we're doing. What we're saying is I want to have S be as large as possible. So we're just going to set it to 0.5. That maximizes that value. But it makes it so that we're not making any assumptions. We're not trying to make that margin of error smaller, or essentially we're not trying to make that n smaller than what would give us the correct answer. All right. So let's take a look at this. Again, determining the minimum sample size that we need for this distribution. We want to be 90% confident within 4% of the true proportion, and we are not given any previous data to pull from. So exactly the same thing. We need our z-score. We need our S, which is the square root of P hat times Q hat. And we need our error. What is the z-score that works with a 90% confidence interval?
Oh,
1.64. That feel familiar?
yeah, 95% is 1.96, that has to be low.
99%, 2.58. Those are kind of the bread and butter three that you could be asked. But again, if we don't know it, how do we find it?
Second one.
Inverse norm with 0.9001 and 7. Okay. What are we saying is true about if we don't know what P and Q are? How do I make S as big as possible? What do P and Q need to be?
Each 0.
They need to be equal. They're both going to be 0.5. So this is going to be 0.5 times 0.5, taking the square root of that. That's as big as we can make S. And then how much error are we trying to aim for? 0.0. 0.0. Okay. So n should be equal to our z-score, so 1.64 times the square root that we're getting, 0.5 of 0.5 divided by 0.04, and we are squaring this up. This is, we saw this on the quiz. This is the formula that I will give you, or that you will be given on the SDC that I will give you for. All right. So parentheses, point fraction, 1.64 times the square root of 0.5 times 0.5 divided by 0.04 squared. This is 420.25. And here's a good lesson in what I was talking about before. what is my actual value of n that I could see? 421. Because even though mathematically 420.25 rounds down, 420 is lower than the minimum n that we are allowed to have, and so we always go to next setup. Questions with unit 6? Feels fine. Pretty easy, maybe not easy, but at the very least, hopefully, if we are given the formulas, we will be able to.
So will you like give us the formula just on the day of the exam or?
I mean, you can Google SDC statistic probability statistics formula sheet. That's what I did. I got them. The same one that we've been using on the test and the last quiz. Yeah. Yeah, absolutely. So we have a fair bit of time, about 45 minutes left. There is, if you did not finish it from yesterday, the 6.2 handout, I think most people got that turned in, but if you have not yet, make sure that you finish that by the end of the day today.